Welcome to the second training module, titled The Decision-Making Process. This module aims to present how to implement a decision-making process based on both the CESBA-SB tool and the SN tool in order to set up high-quality energy retrofitting or new reconstruction projects as part of sustainable urban development plans. Let us start this training by defining what we mean by a decision-making process. It is fundamentally an integrated process for selecting and prioritizing energy efficiency and sustainable retrofitting interventions for significant performance improvements in the rehabilitation of buildings and urban areas. The model of the decision-making process is intended to support public administrations in the definition of two main aspects. Primarily, the best retrofit concept for existing or new urban areas, and secondly, the best retrofit or design concept for public buildings in the context of their urban area. As we are going to see on this slide, the decision-making process is articulated in 6 main phases. So first we find the initiation, then the preparation, the diagnosis phase, the strategic definition phase, the decision-making phase, and finally the retrofit or new development concept phase. Test results form a fundamental part of the retrofit strategy. In fact, the decision-making methodology makes use of test protocols in order to generate 9 retrofit concepts for pilot urban areas, with the support of CESBA local committees. In the following slides, we will be going through the different phases of the decision-making process. We'll start with the initiation, particularly the selection of the area under consideration. In the initiation phase, one selects an urban area and 2 public buildings. This is particularly necessary to set clearly the physical boundaries of the urban area. The physical boundaries of the urban area may be derived from the following criteria, which are listed below, such as the geographical proximity, property ownership or occupier, social and economic context, legal and administrative boundary lines, period of construction, and finally the energy supply infrastructure. An example of this is clearly shown on the slide, where the different areas considered are marked in different colors so that one can distinguish between one and the other. Moving on with the decision-making process, we now go into the second phase, which is the preparation phase. In particular, as one can notice on this slide, one needs to consider both the urban scale and also the building scale, while referring to the current state of both these two. As already introduced in the first training module, the generic framework contextualization is used to select a number of criteria which are then weighted by means of priority factors and weight adjustment benchmarks so that these are finally fed to both the SN tool and SB tool in order to get an assessment on both the urban scale and also the building scale. As part of this second phase within this decision-making process, one would need to identify important information sources for each indicator. In fact, a high-quality retrofitting concept can only be achieved if it is planned on a solid basis. In fact, here we see a number of information sources which can be useful in order to guarantee such a high-quality retrofitting concept. In fact, one can mention administrative bodies of municipalities, building owners or tenants, existing EPC certificates, energy supply companies, public accessible free source data, such as that accessible from Google Earth or OpenStreetMaps, on-site inspection by planners, and finally default data sources and databases which one may obtain from other research and development projects. In fact, in this slide, one has an example from the city of Torino, in which we are seeing the different sources which can provide us with the necessary information for the different areas highlighted before. So, for example, if one goes to the city planning head office, one can get cadastral maps, updated numerical cartography, zoning plan of the city, and so on and so forth. If one goes, for example, to the green head office, one can get the site plans of the green areas, the urban green plan, and so on and so forth. So here we have sort of an indication of the different places one would need to look in order to obtain the required information to actually get more information about the indicators mentioned before. An important tool to be used is a so-called geographical information system, as the one shown here on the slide. This particular GIS tool is called Quantum, and in fact it is important to elaborate further the data one has in hand. In fact, it allows the acquisition, the analysis, and the visualization together with the restitution of such information which is deduced from geographical data, sometimes referred to as georeference data. So moving on to the third phase, which is called the diagnosis phase, we will see that after the preparatory phase, we will be able to actually characterize the building and urban area and eventually identify the current state of our urban scale and building scale environment. In particular, this phase consists in the evaluation of the actual performance and level of sustainability of the urban area and buildings. The diagnosis phase, in fact, identifies the strengths and weaknesses of the whole urban area and public buildings in terms of sustainability. And in doing so, it sets the basis for the definition of the performance targets for the retrofitting project of both the urban area and public buildings. In this third phase, the SESBAMET committees should be highly involved by having access to the results of this phase. Especially the municipalities or local councils, as well as the owners and tenants, should participate in this phase. In order to properly carry out this diagnosis phase, a SWOT analysis is recommended to be undertaken in order to identify the strengths, weaknesses, available opportunities and possible threats at urban level. In fact, what we see here are typical strengths, weaknesses and opportunities together with the threats of a particular urban level environment. So, once the diagnosis phase is completed, one would need to move to the next phase, which is the fourth phase, called the strategic definition, in which one, based on what have been done already, would set the constraints and target the definitions. So in the next couple of slides, we will be looking at setting targets, looking also at the constraints and the limitations that one would have. So let us first start by looking at what targets one needs to set. So before starting to create a sustainable retrofitted scenario for an urban area and buildings, it is fundamental to define clear and measurable targets that should be achieved by the retrofitting concept. Seneca said 2000 years ago that if one doesn't know to which port one is sailing, no wind is favorable. And this is a very valid quote in this scenario. In fact, targets must address all fields of sustainability like environment, economy, and social aspects amongst other things. So let us now go in more detail on these three main aspects. So if we start with the environmental targets, the environmental targets may address the following fields, like for example, improve the energy performance, reduce greenhouse gas emissions, increase the share of renewable energy being used in that district, foster the use of sustainable materials, and also reduce soil sealing and increase available green spaces. From the social aspect, social targets may address the following fields like avoid gentrification caused by energy retrofitting of buildings, improve district surroundings such as green spaces, heat island and accessibility, improve the transport infrastructure and mobility, together with improving the safety and security and support participation and local activities versus a district which is actually dormant. Another target, and which is also an important target, is the economic target, which may address the following fields such as affordability of housing rental, labor force participation, fostering the value of conservation, and enhance an increase in the property value. Above all, targets need to be smart. Nowadays, this word is often overused, but in this context, SMART is also an acronym which refers to the following. So the S refers to specific, meaning that the target must be clearly defined and not vague, but as specific as possible. It should be measurable, that is, that targets must be quantifiable by some means. Attainable, such that a target must be realistic and achievable. It should be relevant, that is, targets should be relevant for energy retrofitting of urban districts. And finally, it should be time-bound, that is, it should specify when the results can be achieved. To get a clear direction in which the sustainability retrofitting projects for the urban area and the buildings should be developed, the target issues have to be transformed into measurable performance targets. A target for each indicator must be fixed in both the SN tool and SB tool to reflect the environmental, social and economic targets. So for example, here we are seeing two particular indicators, for example, the permeability of the land. So at current state it is at 15% and we set a target for 25%. Another example would be the availability of safe bicycle routes. For example, in this case we are given an example in which in the current state we have an 8 meter per inhabitant of availability of safe bicycle route, whereas the target value we're going to increase that by 4 meters per inhabitant such that we get a target value of 12 meters per inhabitant. We now move on to set the constraints and restrictions. In fact, the main constraints that occur in district and building sustainability retrofitting projects are listed here. So, amongst these we find the legal constraints, including the building codes, cultural heritage protection, and so on and so forth. Technical constraints like architecture and system, financial constraints, environmental condition constraints, and finally stakeholder-based restrictions. So let us go in more detail on each and every of these constraints. So let us start with the legal constraints. So in particular, legal constraints are generally given by regulations for energy savings in buildings and laws on cultural heritage protection. So legal constraints may give us restrictions to many retrofitting technologies that, although theoretically available on the market, cannot be applied. So, in order to keep the cultural value of the buildings and districts, one would be sort of have a restriction not to be allowed to achieve the improvements required to the insulation, for example, of the building envelope or the installation of photovoltaics that in theory could be technically feasible, but because there are laws on cultural heritage protection in order not to damage these buildings, that this would not be possible. Moving on another constraint, we encounter technical constraints. These are restrictions for the use of technologies in building energy retrofitting projects. Each retrofitting technology needs special requirements for its implementation, which may not always be given by each building or district. What do we mean here? So, if planners want to use a geothermal heat pump with ground collectors, the property on which the building is located must have enough space for laying the ground collectors. According to the needed output of the heat pump, the space may not be available in a dense urban areas, thus restricting the use of such technology. The use of renewable energy supply systems like biomass boilers needs enough space to store the biomass. So this is another example in which a technical constraint may limit us on what technologies we can use. Another important constraint, which is often the largest obstacle in energy retrofitting projects on building and district level, is the financial constraint. Planners often have to consider the financial situation of the building owners, as well as the tenants, in order to avoid negative social impacts such as gentrification. In addition, depending on the type of owners, given if they are private or public, the economic efficiency of the retrofitting technology is also considered as a big issue. So, other important constraints are those related to environment. In fact, they are called environmental constraints. Here we have a couple of examples. So we could mention, for example, those related to climatic conditions, in which particular climatic conditions are not suitable for the use of certain technologies like solar energy systems or wind power. Another example could be the condition of the ground can also restrict the use of geothermal systems. The availability of biomass sources near the district can also be a limiting factor for the use of biomass boilers. And finally, the feasibility of solar energy systems and roofs and facades is also dependent on the solar radiation exposure of the area. So, moving on with our phases, we now come to phase 5, which is the decision-making phase, in which we filter out solutions from the given constraints and look at potential scenarios and actually rate these scenarios. So let us give more details of what we mean by this. So the fifth phase consists in the study of possible alternative retrofit scenarios for the pilot urban area and the 2 public buildings selected. In addition, one would need also to identify the best solution in terms of cost efficiency. In particular, this is done in 2 steps. First, by creating the retrofitted scenarios, and then retrofit concepts are assessed and ranked in order to actually take the final decision. So let us start with the first stage of this process, which is the creation of retrofitting scenarios. The goal of each concept is to optimize the performance of the urban area as a whole, considering all buildings as a global system connected by the following processes, which are listed below, such as the selection and optimization of energy intervention package at urban level, the selection and optimization of energy intervention package on building level, the addition of non-energy related interventions such as traffic, mobility, green spaces and infrastructure, the inclusion of business models and financial schemes, and finally the approval of design variant. So the creation of retrofitting scenarios should follow a chronological sequence in order to create an efficient and complete energy retrofitting concept. One would first start with the reduction of energy consumption, which should be consumer driven. In fact, the reduction of the energy consumption is the basis for the creation of sustainable energy concepts and to achieve the set sustainability goals. For that reason, the reduction of the energy consumption must be the first priority for the planners. Then we move on to the second part of the sequence, which is related to increasing the efficiency of the energy supply. And here we say that district solutions should be preferred over individual solutions to have a more holistic approach. Finally, the third part of this sequence is the inclusion of renewable energy production, and this is done to increase the share of climate neutral and renewable electricity in a district in order to have a reduction in the primary energy consumption as much as possible. What we have presented before is now represented as a pictogram in which we see the different scales of interventions at the energy consumption reduction stage, the energy efficient supply stage, and the renewable stage, in which we see at which level one would need to intervene, either at building or both neighborhood or building level. An adequate analysis and evaluation is required in order to find the most optimum solution for a particular district. There are a couple of points that one needs to look at. So let us start with the first point, which is related to assessing the energy weak points of a building. So in order to prioritize different retrofitting measures to reduce the energy consumption and to increase the energy efficiency of a building, it is necessary to know which represent the weakest points of the building from energy point of view. Secondly, one needs to assess the feasibility of the energy networks. So the use of synergies between buildings is one of the most promising and useful key strategies for urban district retrofitting projects. One of the main advantages of the district approach compared to the individual retrofitting measures on single buildings is the use of heat-related synergies by the connection of buildings. Another point is the assessment of the electricity-related synergies and interactions between buildings. Renewable energy sources are climate dependent, and the electrical consumption is not. Thus, more often, a mismatch between the supply and demand occurs, and the generated energy cannot be fully used when the demand is there, which in turn has a negative impact on the reliability and the efficiency of the whole network. To overcome this challenge, planners need to be able to predict the electrical demand and production by renewable energy sources for the investigated district in order to produce appropriate energy storage systems or smart grids. So moving on to the financial aspects, so financial planning and selection of financing mechanisms for the implementation is also key. For each retrofitting concept, adequate business models and financing have to be selected in order to implement it in practice. Moreover, financial metrics like investment cost, return on investment, and payback need to be accurately calculated in order to ensure the financial feasibility of each concept. So let us go into more detail on the financial planning aspect and looking at the different mechanisms that could be employed in order to finance a particular project. So first we start with grants. So grants may be available at all stages for feasibility studies, proposal development, capital investment, and maintenance expenses. They offer a subsidy to the total costs, but exist only because governments or other organizations wish to see particular innovations developed that would otherwise not be economically attractive. Loans are another means how one can finance a project, but of course, as one can understand, loans imply debts that must ultimately be repaid, and ongoing interest charges may affect the development of the project. Retail and commercial banks will generally lend, but at a price that depends upon perceived risks. Loan guarantees is another ancillary financial project that can be used to reduce the cost of debt finance. Essentially, it involves another stakeholder to the project investment team, which is generally called the loan guarantee. The loan guarantor is usually a public body created to lower the cost of energy-efficient loans, acting as a financial guarantee that defaults will be avoided. The following are two other financing possibilities that one can adopt. These are mainly energy performance contracting and co-investment. Energy performance contracting is usually undertaken by a so-called ESCO or energy service company through a contractual obligation to implement the energy savings initiatives in return for a flow of payments from the building owner or end user. With respect to co-investment, there are several initiatives around the world whereby municipalities or energy utility companies assume the capital cost of retrofitting and place the charge on the property to be recovered through the regular property tax or utility bill assessment and collection. Fiscal measures are also an important class of support and can relate to a reduced rate of tax for the owners, properties, and contracting organizations, as well as specific tax and VAT benefits on the various cost or revenue elements. Evidently, these are particular to the individual EU member states but are widely used as part of the business models. Finally, embedded revenue contributions are another form of support or funding mechanism. Many countries now encourage residential, commercial and industrial consumers to install solar, wind, biomass, microhydro and other renewable sources of energy to reduce the consumption of grid-supplied energy for sale back to the local distribution company, or in the case of larger industrial units, to the wholesale market. These feed-in tariffs, sometimes called FITs, arrangements vary according to the technology, vintage, length of term, and size of connection. District-level solutions have a lot to offer here, as there are economies of scale in the provisions of generating facilities and transaction cost. This is particularly important to emphasize the fact that if one looks at the district level rather than the building level, one can possibly have a more economically viable solution than the building counterpart. Finally, the set scenarios should be assessed and ranked. This is where the SN tool and the SB tool come in useful. In fact, these tools allow the planners to compare the different retrofitting scenarios that have been created and to find the best suiting one for the local preferences. In fact, SESBAMET tools assessment system have to be applied to each retrofitting scenario at both urban scale and interactively at the building scale to evaluate the performances reached. On the basis of the assessment's outcome, which are given in terms of scores, provided by the SESBAMET assessment tool, it will be possible to rank the different retrofitting scenarios according to the preferences of different stakeholders and decision makers. As an example, here we see how the SESBAMET tools can be used to compare at different levels. Here we see the different levels which we have already discussed and gone through in training module 1, in which the current state of the urban system is analyzed and two possible scenarios are compared by means of this tool. So we are finally coming to the end of the decision-making process. In fact, we are now at the sixth phase, which is called the retrofit or new development phase. This phase, in fact, consists in the description of the retrofit concept being applied for the pilot urban area and the two chosen public buildings, based on the best ranked scenarios. The concept will further specify the solutions taken into account by the best scenario. The concept will be ready to be implemented in the future when the conditions will allow such a project to be transformed into reality. The concept will mainly illustrate the retrofit strategies, the performance improvement that will be achieved, and the cost-benefit analysis. So, as a summarizing and concluding slide to this second training module, we present a pictogram which shows that the sustainable urban neighborhood regeneration concept is centered around the concept of energy retrofitting, which doesn't stand alone but is related to many other aspects which affect both the urban level and the building level. And amongst these, one can mention, for example, social stability, water protection, architecture and design, economic growth, spatial development, improvement of quality of life, traffic and mobility, and finally, nature and climate protection. Whilst thanking you for your attention, we encourage you to follow up the next training module 3.